Swayam Prabha. Digital India. Educated India.
Start our discussion on the third types of synthesis, that is function generation. Function generation, we mean how to maintain the specified relationship between the input and output movements. We shall take the example of a 4R function generator with 3-position synthesis. 3-position synthesis, we mean 2 pair of coordinated movements of the input and output links, namely theta 2 1 2 and theta 4 1 2, where theta 2 represents the orientation of link number 2, which is the input link, and theta 4 represents the orientation of link number 4, which is the output link. This theta 2 and theta 4 can be measured from some reference line, say the line of frame O2, O4. Now, let us look at this superscript. What we say, theta 2 1 2, that is the change in the value of theta 2 from position 1 to position 2. That is, theta 2 1 2 is nothing but theta 2 2 minus theta 2 1. The superscript 1 and 2 refer to the 2 configurations 1 and 2. For 2 pair of coordinate movement, this is 1 pair, that as the linkage moves from configuration 1 to 2, and theta 4 1 2 similarly is theta 4 2 minus theta 4 1, that is the output movement from configuration 1 to configuration 2. So, there is a prescribed value for this theta 2 1 2 and theta 4 1 2, which we have to satisfy by designing the 4R linkage. Similarly, the movement of the input and the output links from configuration 2 to 3 described by theta 2 2 3 and theta 4 2 3 are also prescribed, which have to be satisfied. Let me now explain these symbols with reference to a figure, and then explain how to graphically synthesis the 4R linkage such that these 2 pair of coordinated movements are achieved. This figure explains the symbols that we have just now talked about for 3-position synthesis of a 4R function generator. Let O2 and O4 are the 2 fixed pivots that defines the line of frame O2, O4. The input link is O2A. Now, as this input link moves from position 1 to 2, the rotation is theta 2 1 2. So, if we measure theta 2 from O2, O4, then this angle, that O2A2 makes with O2O4, we call theta 2 2. This superscript 2 refers to the second configuration. Similarly, the angle made by O2A1 is theta 2 1. So, theta 2 1 2 is theta 2 2 minus theta 2 1. This is the movement of the input link as the linkage goes from first to second configuration. Corresponding movement of the output link is also prescribed as theta 4 1 2. Similarly, as the linkage goes from the second to the third configuration, that is the crank pin goes from A2 to A3, the rotation is theta 2 2 3. That is theta 2 3 minus theta 2 2. The difference of these 2 angles, that is the movement of the input link from second to third configuration, that is theta 2 3, theta 2 2 3, that is also prescribed. And we desire that the corresponding movement of the output link should be theta 4 2 3. So, we can easily see that this whole angle, which is theta 2 3 minus theta 2 1, that is this angle, I can say theta 2 1 3. I would ask you to note the superscript. 1 3 means theta 2 3 minus theta 2 1. 23 means theta 23 minus theta 22 and so on. So, to solve this problem, that is to satisfy these two pair of coordinated movements, theta 212 must generate theta 412 and theta 223 must generate theta 423. We proceed as follows. We assume the locations of O2 and O4, the fixed pivots according to our convenience. We also choose the crank pin A1 arbitrarily. The only thing remaining is to determine the location of B1, the other moving hinge, such that O2, A, B, O4, the 4R linkage is completed. To do this again, we apply the principle of kinematic inversion. If we want to locate the point B1, then we should hold link 4, that is the follower link, fixed at its first configuration and allow this fixed link O2, O4 to move such that the same relative movements are maintained. Accordingly, we find the inverted positions of the point A, that is A1, A2 and A3. Since we are holding link 4 fixed, that is the point B is not moving from B1, the point A must move in a circle with BA as radius. As we have seen earlier, first step is to determine the inverted positions of A1, A2, A3, holding the link 4 fixed at its first configuration. To do this, we proceed as follows. So, let me now first choose the fixed hinges O2 and O4 arbitrarily. This is O2 and this is O4. We also choose the first position of the crank pin A arbitrarily, say here, which I call A1. Because the rotation of the input link O2A is prescribed, I can find the second position of the crank pin, which I call A2. So, the rotation of the input link from first to second configuration, which is given to us, is the angle between these two lines, namely O2A1 and O2A2. This is the angle of rotation theta 212. Similarly, the third position is also known because theta 223 is prescribed and A2 comes to A3. This is the third position of the crank pin A3, and the angle between O2A2 and O2A3 is theta 223. This point is O4. So, the only thing remains is to locate the point B1 such that the theta 412 and theta 423, the coordinated movements of the follower, can occur. To do this, we have decided to hold the follower fixed at its first position. Accordingly, to maintain applying the principle of kinematic inversion, that is to maintain the same relative motion, the fixed link O2O4 must rotate by an angle minus theta 412. O4B has been held fixed, so O4O2 moves in the direction opposite to theta 412, which was counterclockwise. So, this angle is minus theta 412. By minus I mean clockwise, because theta 412 was counterclockwise. So, this is the inverted position of O2. Inverted position corresponding to the second configuration, inverted on the first configuration. And the angle between O2O4 and O2A2, which is this angle, that is theta 22. So, if I draw that, I can find the inverted position of A2 inverted on the first configuration. The superscript always refers to the configuration which has been held fixed. Here O4B1 has been held fixed, that is the follower is held fixed at its first configuration. So A1, which is identical to A11. Now, if we look at these two triangles, namely O4, O2, A2 and O4, O2, 21 and A21, what we see that this length is same as this length, because that is the length of the fixed link. This length is same as this length, because that is the crank length, and this angle is same as this angle, because both of them are theta 2, 2. Consequently, these two triangles O4, O2, A2 and this triangle O4, O2, 21 and A21. These two triangles are identical, because two sides and the included angle are same. So we get O4, A21 is same as O4, A2. In fact, what has happened, this whole triangle has been rotated by the angle minus theta 4, 1, 2. So we can say I can go from A2 to A21 by rotating O4, A2 through an angle minus theta 4, 1, 2. This is the principle of getting the inverted position of A2 inverted on the first configuration. Exactly the same logic can be applied to get the inverted position of A3 by rotating O4, A3 about the point O4 this I will call A3, 1, and O4, A3 is rotated by minus theta 4, 1, 3. So we get the three inverted position A1, which is A11, A21 and A31, and B1 is nothing but the center of the circle passing through these 3 points. So I can easily determine where B1 is. Drop a perpendicular bisector of this line. This is the perpendicular bisector. Similarly, drop a perpendicular bisector of this line A21, A31. This is again perpendicular. So these two perpendicular bisectors meet at B1, that is B1 is the center of the circle passing through A11, A21 and A31, and we have designed the required linkage as in this first configuration as O2, A1, B1, O4. So we get the required 4R linkage to generate the two prescribed pair of coordinated movements of the input and the output link. O2, A1, B1 is the required linkage. Let me go through the procedure once more. O2 and O4 were chosen arbitrarily. A1, that is the location of the crank pin at the first configuration, was chosen arbitrarily. From the given movements from the first to the second configuration of the crank, I can locate A2 and A3 on this circle with O2 as center and O2 A1 as radius. A1, O2, A2 is angle theta 2, 1, 2. A2, O2, A3 is the angle theta 2, 2, 3. Now we apply the principle of kinematic inversion, hold the follower fixed at its first configuration, which means the fixed link will rotate in the opposite direction by minus theta 4, 1, 2 and minus theta 4, 2, 3 to get the corresponding inverted positions. So O2 goes to this point, which I have called O2, 2, 1. That is the second position inverted on the first configuration. By rotating this link O4, O2 about O4 through an angle minus theta 4, 1, 2. Now theta 2, 2 is known, that is the angle between O2, O4 and O2, A2. So I draw the same angle theta 2, 2 between this line O4, O2, 2, 1 and O2, A2, 1. I get the point A2, 1. Then using simple geometry, we could prove that I could have obtained A2, 1 simply by rotating O4, A2 through an angle minus theta 4, 1, 2. O4, A2, this is the line. I am rotating through an angle minus theta 4, 1, 2, and we automatically get the inverted position A2, 1. Similarly, by rotating O4, A3 through an angle minus theta 4, 1, 3, I get the inverted position of A3 as A3, 1, and finally B1 is obtained at the center of the circle passing through these 3 points, namely A1, 1, A2, 1 and A3, 1. Next, we will take an example of a slider crank mechanism such that can be used as a function generator, that is the output link, that is the slider movement is coordinated with the movement of the input of the crank. So let us now discuss the slider crank as a function generator, where we treat the slider as our output link and crank as the input link. If we talk of 3 position synthesis, as we have seen in the case of a Fodor linkage, we mean 2 pair of coordinated input-output movements. That means we have to design a slider crank such that the crank rotation theta 2 from position 1 to 2, that is theta 2, 1, 2, must generate a slider displacement in a particular direction. We shall take it to be horizontal, say S1, 2. So this pair is prescribed, theta 2, 1, 2 must generate S1, 2. Similarly, theta 2, 2, 3, that is from the second to the third position, must generate slider displacement S2, 3. So these 2 pair of coordinated input-output movements are prescribed, and we have to design the required slider crank mechanism. So this diagram explains the 2 pair of coordinated movements for a slider crank. Theta 2, 1, 2, this amount of clockwise rotation of the crank must produce S1, 2, this much of horizontal displacement of the slider. Similarly, theta 2, 2, 3, that is from position 2 to position 3 of the crank, this amount of rotation should generate S2, 3, this is the amount of horizontal sliding movement of the slider. Our job is to find the required slider crank mechanism. As before, we assume the crankshaft location O2 according to our convenience. We choose it arbitrarily. We also choose the crank length and the crank pin corresponding to this first configuration. If I call it configuration 1, we choose A1 at this location. So we call this A1. So using this information theta 2, 1, 2 and theta 2, 2, 3, I can rotate O2 A1 and get the corresponding locations of A, which I call A2 and A3. The only thing remaining is where should be the slider corresponding to the first configuration, that is the other moving hinge connecting the connecting rod and the slider, which we call B1. To determine B1, we must hold the slider fixed and consider the kinematic inversion. The same relative movements between the crank and the slider, but we hold the slider fixed and allow the fixed link to move. So if we hold the slider fixed at the first position, then corresponding to this movement of the slider, the fixed hinge will move opposite to that by the same amount, so it should come here. And this we called O2 second position inverted on the first position. And we also know that the angle between the horizontal line through O2 at the A2 position, second position. So we draw here at the same angle and we get the position, inverted position of A2 we call A21. A1 and A21 are coming out to very close. As we have seen in case of the 4R linkage, A21 can be easily obtained by sliding A2 by minus S12. A2 you move to the left because S12 is to the right, minus S12 is to the left. So I move horizontally the point A2 and I get to A21. Similarly, this whole distance S12 plus S23, this whole distance is what I call S13, that is to the right. So holding the slider fixed, we move the fixed link and the crank to the left. So A3 I move by minus S13 to the left and get to this point, which I called A31. So holding the slider fixed at the first configuration B1, because the connecting rod is a rigid member, the length AB remains fixed. So A1, which is nothing but A11, A21 and A31. So we have got 3 points here, A11, here A21 and here A31. Now we can easily find the center of the circle passing through these 3 inverted positions of A, and we get the point B1. Accordingly, I have designed the slider crank mechanism, required slider crank mechanism as O2 A1 B1. O2 A1 B1 is the required slider crank mechanism such that when A1 goes to A2, B1 will move to the right by S12, and as A1 goes to A3, this slider will move again to the right by a magnitude S23. As we have seen, we assumed arbitrarily the location of the crankshaft O2 and the crank pin A1. Only determine the slider location corresponding to the first configuration at B1, this revolute pair. We have solved the problem also by choosing arbitrarily B1 and find A1. That is what we will do in the next example. The same slider crank mechanism I will try to design, but assuming the location of B1 arbitrarily and find the required position of A1. I would ask the students to solve the 4R function generator the same way. Instead of choosing A and determining B, one can also solve the problem by choosing B and determining A. Of course, then we have to hold the input link, that is the crank fixed, and apply the principle of kinematic inversion, as we shall explain just now with respect to this slider crank mechanism. Let me now say this design of the slider crank mechanism to generate these 2 pairs of coordinated movements as we have seen in the previous problem. It is the same problem, only thing we solve it a little differently by assuming the crank pin location arbitrarily, say here, which we call O2, and we assume the other moving hinge which is connecting to the slider at the first position is here, which I call B1. To generate these two movements S12 and S23, B1 must move to B2 and B3. B2, B3 is S23. Only remaining task is to locate the crank pin A1. So, to determine that, we hold the crank fixed at its first position such that the point B moves on a circle with A1 as the center. So, we have to first find the inverted positions of B2 and B3 if we hold the crank fixed at its first location and apply the principle of kinematic inversion. As we see, the fixed link is represented by this diagram. This is the fixed link on which the slider is moving to the right. So, if we hold the slider crank fixed, then this fixed link should rotate by minus theta to 1, 2. That is, it should rotate, the crank is held fixed, so O2 point is not moving. So, this fixed link is rotating counterclockwise by theta to 1, 2, which I call minus theta to 1, 2. So, the fixed link is now represented by this line. And point B2 is at a distance from here by so much. This is the distance of B2 from this point. So, from this point I take this distance and I get to this point B2, which is nothing but B21, inverted position with the position 1 being held fixed. So, that, as we see, we can easily do by rotating O2 B2 through the same angle. This is O2 B2 is rotated by minus theta to 1, 2. Similarly, by rotating O2 B3, this is the line O2 B3, this was the line O2 B2. So, this whole angle is minus theta to 1, 3, which is theta to 1, 3 is this angle, which is clockwise. So, I rotate counterclockwise, and we get to the point by rotating O2 B3, I get to the point B31, and B1 is nothing but B11. B1 is same as B11. Now, the center of the circle passing through these 3 points B11, B21 and B31 determines the location of A1. We draw perpendicular bisector of these two lines as usual. We draw the perpendicular bisectors. This is perpendicular and this is also perpendicular. These two lines intersect to determine the center of the circle passing through B1, which is B11, B21 and B31, and we get A1. So we have designed the required for slider crank mechanism O2, A1, B1. We have got O2, A1, B1 as the required slider crank mechanism which will generate these two pair of coordinated movements. Only difference in this is that I arbitrarily assume the location of B1 and determine A1. In the previous example, we assumed the location of A1 and determined the corresponding location for B1. Now that we have explained the three position synthesis for path generation and function generation, we can attempt to solve another problem by a two-stage synthesis. Suppose the problem is as follows. We have to design a 4R linkage such that the coupler curve is approximately a straight line. We talk of three position synthesis. Obviously, that problem we could have done by the method explained earlier. Here what we are doing, we are saying it is not only a three position synthesis for a coupler curve which is approximately a straight line, we also want to coordinate it with the input movement. That means that as the coupler point goes from first position to second position, the crank must rotate by a specified amount. Similarly, as the coupler point goes from the second to third position, we want the crank to rotate by again a specified amount. To solve this problem or coupler curve generation, of course, an approximate straight line coupler curve generation coordinated with the input movement can be solved in two stages, which will be explained now. To solve this problem, first we design a slider crank mechanism. This is the slider crank mechanism such that this pair of coordinated movement from first to second configuration and second to third configuration can be designed. This we have done just now. If we specify theta 212, theta 223 and the corresponding S12, S23, I can always design this slider crank mechanism. After designing the slider crank mechanism as a function generator for two pair of coordinated movements, what we do, we talk of the midpoint of this connecting rod. At the third configuration, say it is here. At the second configuration, the same coupler point, same midpoint of the connecting rod is here, and in the first configuration it is here. So we mark this midpoint of the connecting rod corresponding to the three specified configurations as C1, C2 and C3. The center of the circle passing through these 3 points C1, C2 and C3 is here. So what we do, we make that as our O4 for the required 4R linkage. For that purpose, we remove this slider and take this fourth link and put a hinge between that midpoint of the original connecting rod connected by this rigid link whose center is at O4, which is hinged at O4. This is the other fixed hinge. So we have got a 4R linkage, namely O2, A, B, O4. This is designed from the previous slider crank, only the slider has been removed. Now if we move this linkage, what we should see, that this point of the coupler is still following the original straight line, but only approximately. We can notice this, that this coupler point, though not guided by the slider as before, the slider is totally detached, but this 4-bar linkage is also driving this coupler point through the axis of this slot where the previous slider was moving. So we have generated a coupler curve synthesis problem or path generation problem coordinated with the input movement. As it goes from position 1 to position 2, this rotates by a specified amount. As it goes from position 2 to position 3, again it rotates by the specified amount, which was dictated by the original slider crank. So this is what we call a two-stage synthesis. So all the methods that have been taught so far can be cleverly used to design more complicated mechanisms, rather mechanisms with more complicated motion requirements. Let me now repeat this two-stage synthesis problem. What we did, first we designed a slider crank mechanism such that it acted as a function generator. The slider displacement was coordinated with the crank rotation. Then we took the midpoint of this connecting rod at these three configurations, which is C1, C2 and C3, for the three positions which have been generated by this slider crank as a function generator. Then we removed the slider and considered the midpoint of this connecting rod. Corresponding to these three positions, it is at C1, C2 and C3. The center of the circle passing through these 3 points is at O4, so we added a fourth link with O4 as the fixed hinge and connecting it with C1. So we get a 4R linkage with this coupler point generating an approximate straight line as we have seen earlier. And as it goes from position 1 to position 2, the movement of the crank is exactly same as it had with the slider crank. Similarly, the movement of the crank from C2 to C3 is again theta 2, 3, which is coordinated. Now the question is, why did I take the midpoint of the connecting rod? I could have taken any point on this connecting rod and consider the three positions of that particular point and think of the circle